In this lesson, we build an intuitive visual understanding of earthquake-triggered landslides and slope instabilities. When mountains shake, slopes can fail in many different ways, moving huge amounts of rock and soil downslope. We'll see what triggers them, where they happen, which kinds we get, and how they reshape the landscape during and after big earthquakes. First, the immediate trigger is strong ground motion. Shaking reduces the effective shear strength, and cyclic accelerations can exceed what the slope material can resist. When that happens, failure initiates and mass moves downhill. Earthquake-triggered landslides take many forms. Rock falls break free and drop nearly vertically. Rock avalanches and debris slides move as fast, dense flows downslope. Some failures are shallow and skim the surface, while others are deep-seated and detach a thick block. And in fine-grained or saturated materials, we can get earth flows that behave almost like a slow-moving fluid. Historically, global compilations showed simple patterns. Larger magnitude earthquakes affect larger areas and trigger more landslides. Distance from the fault matters too. Near the fault, shaking is strongest and failures are most abundant. More directly than magnitude, ground motion intensity controls failure. Peak ground acceleration, peak ground velocity, and Arias intensity all correlate with landslides. Areas with very strong acceleration, for example above 0.5 g, are usually riddled with slope failures. Slope angle and material matter too. Rock falls often cluster around 30 to 40 degrees, and soil slides around 20 to 30 degrees. Local conditions modulate susceptibility. Weak, highly fractured rock or thick soil mantles fail more easily than strong, intact rock. Water matters too. When slopes are saturated from rain or snowmelt, they are primed to fail under shaking. Co-seismic landslides strip soil and vegetation and deliver debris to valleys. They can even dam rivers, creating lakes that later breach and cause downstream floods. This injects a pulse of sediment into the river network that takes years to evacuate. After the quake, scars remain bare. Rainfall can remobilize the loose debris for several years, producing debris flows that keep the sediment pulse moving downstream. Landslides are not random. They mirror shaking patterns and topography. Near the fault, especially on the hanging wall of a thrust fault, failures are most dense. Sizes range from tiny rock falls to gigantic rock avalanches. The frequency size distribution usually follows an inverse power law: many small, few large. Larger landslides often travel farther down valley, producing long runouts and dramatic geomorphic change. How do we study them? Field surveys map landslide scars and measure failure geometry. Remote sensing compares pre- and post images to build landslide inventories and uses radar coherence change to see failures even under forests. In the lab, shear tests on collected materials help explain rapid strength loss under shaking. With mapped inventories, we use statistics and geographic analysis to relate landslide density to controls like acceleration, slope angle lithology, and rainfall. Simple models compute the probability of failure using a logistic curve of these predictors, which helps rapidly anticipate impacts after new earthquakes. Global databases now compile hundreds of landslide-triggering earthquakes and dozens of detailed inventories. These data drive empirical models that forecast total landslide counts and affected area, supporting rapid response. To summarize, earthquakes in steep terrain commonly trigger thousands of landslides, especially near faults and in areas of very strong shaking. Slope angle, rock and soil strength, and water content modulate where failures occur. The geomorphic impact is immediate and long-lasting, from hill slope stripping to river damming and prolonged sediment pulses. Field mapping, remote sensing, lab tests, and statistical models together help us understand, map, and anticipate these cascading hazards. Thanks for learning with us.